So I'm going to talk about some old results and some new results with a variety of past and current students at the University of Texas. There we go. And it's going to be about theories of class S, and I'm glad that Monica gave a nice review yesterday, which will ease things today. Class S theories are obtained by taking 60 2-0 superconformal field theories, compactifying them on a punctured Riemann surface in some appropriate way, and you obtain a 4D n equals 2 theory out of that. And in the untwisted case, these theories typically have a conformal manifold. They're superconformal theories in a continuous family where that conformal manifold is the moduli space of the punctured Riemann surface that we compactified on. In the twisted case, which is actually going to be what I'm going to be talking about today, things are a little bit more complicated. First of all, if you have an ADE Lie algebra, there's an of types A, E, or D, A, E6, or D. There's outer automorphisms. And as you go around some cycle on the Riemann surface C, you can twist the theory, the 60 theory, by that outer automorphism. And that gives you some new class of 4D n equals 2 theories, which we might call twisted class S. And for the Lie algebras, A, E6, and Dn for n not equal to 4, the outer automorphism group is Z2. But for D4, this is the subject of all of the fun, the outer automorphism group is non-abelian. It's the permutation group on 3 objects, which you can, here's a presentation of it. It's got one generator which squares to the identity, another generator that cubes to the identity, and they obey this relation over there. And what they do on the Lie algebra of D4, alpha swaps these 2 roots, and beta cyclically permutes the simple roots. So this is hopefully familiar. But it leads to some rather interesting complications, including some new and somewhat exotic conformal manifolds. So that's what I'm going to be the focus of this talk. So let's first talk about the untwisted case. The simplest thing you can do is think about one complex dimensional conformal manifold. So there are 2 cases, either the 4-punctured sphere or the once punctured torus. And for the 4-punctured sphere, which will be the subject of much discussion during this talk, the moduli space of the 4-punctured sphere is the upper half plane modulo the congruent subgroup gamma of 2, where gamma of 2 is the subgroup of PSL2Z generated by those 2 generators, T squared and ST squared S. And the compactified moduli space, and I'll dwell on why I want to think about the compactified moduli space in a bit, is just a copy of CP1. So the degenerations of the curve correspond to the point 0, 1, and infinity, where the coordinate on this moduli space, the conformal manifold of the theory, is a certain ratio of 4th powers of theta functions. Okay? And I want you to remember that 4th power of theta functions, because it's going to appear on just about every slide that follows. Sorry? It's a help bundle for that congruent subgroup, right? Indeed. In the Z2 twisted case, roughly speaking, we're interested in the moduli space of pairs consisting of this punctured Riemann surface and a Z2 principal bundle on it, or equivalently, this punctured Riemann surface and an element. What? I lost the microphone already? Okay, let's, wow, okay. And an element of H1 of the curve with Z2 coefficients. Okay, a non-zero element of H1, right? And I want, but there are a few caveats if you want. So I'm going to fix the bundle restricted to a little circle surrounding each of the punctures, right? So it's either trivial, in which case I call the puncture untwisted, or it's the non-trivial Z2 bundle, in which case I say this is a twisted puncture. And what I get when I do this is some kind of branched covering of the moduli space where I forget about the gamma bundle. That's not quite right for the Dn case because the outer automorphisms of D2n act on the set of nilpotent orbits. As Monica reviewed, the punctures are decorated by a nilpotent orbit of the Lie algebra. And there are a set of orbits in D2n which are very even. So nilpotent orbits are in Dn are labeled by partitions of 2n, or in D2n by partitions of 4n. And if all of the parts are even, there are actually two nilpotent orbits, and they're exchanged by the outer automorphism, right? So we get a further ramification if I have untwisted punctures of this sort, because when you go around, drag that puncture around some cycle on the Riemann surface, it might come back to its partner under this outer automorphism. And I want to remark that it's important for me to include the boundary. I mean, the boundary for physicists is great because that's where weak coupling happens. And if there's anything we understand, it's weak coupling. So we totally should study that as part of our space of theories. But it's really important in these twisted cases because there are, whereas generically there's a decoupling of degrees of freedom that happens at the boundary because some gauge coupling goes to 0. There are, in these twisted theories, there are situations where that doesn't happen and there's no decoupling, and the boundary of MGN ends up being somewhere in the middle of the conformal manifold as opposed to on the boundary of the actual space of physical SCFTs. You'll see that spelled out in detail in a bit. But in any case, we get new, as I said, we get new conformal manifolds fibered in interesting ways over the moduli space of punctured Riemann surfaces. So to kind of fix ideas and show you some of the weirdness that can happen, let me give you, start with a particular example, not in type D, but in type A, so the twisted SU2N theories. And I'll study not a 4-punctured sphere, but a 5-punctured sphere. So the untwisted punctures, there will be 3 of them, 2 in the subregular nilpotent orbit, that's the so-called simple puncture, and 1 of them in the 0 orbit, that's the so-called full puncture. And then I'll have 2 punctures in the Z2 twisted sector, which are in the regular nilpotent orbit of SO2n plus 1. That's the way those things are labeled, as Monica so beautifully reviewed last time. And the moduli space of the 5-punctured sphere, the compactified moduli space of the 5-punctured sphere, is a certain complex surface which goes by the name of del Pezzo 4, and it projects to 2 copies of CP1. So naively, you can say I have these 5 points, I'll fix 3 of them to 0, 1, and infinity, and then the locations of the other 2 are the moduli, so call them S1 and S2. And so there's a projection, so S1 is the coordinate on here, S2 is the coordinate on there, and the only thing we need to do to get the actual moduli space is blow up 3 points. Okay, so the actual moduli space is CP1 cross CP1 blown up at 3 points, also known as del Pezzo 4. And this theory locally looks like 2 decoupled copies of a familiar theory with familiar class S, untwisted class S realization, namely SUN with 2n hypermultiplets in the fundamental representation. So you might expect that what I should get is two decoupled copies of this theory, whose conformal manifold is then a direct product of two copies of the conformal manifold of one of them, namely, as I said, the upper half plane mod gamma of 2, right, or the moduli space of the four-punctured sphere, with f of tau, remember, ratio of fourth power of theta functions, with respect to tau 1 and with respect to tau 2, right? That's what you expect, right? What we actually get in this realization is something slightly more interesting. So our actual conformal manifold, I'll call it M bar, has a projection to the moduli space of the five-punctured sphere, and it has a projection to the moduli space of two genuinely decoupled copies of the aforementioned Lagrangian field theory. But it's actually the quotient of two copies of the upper half plane by some group G that sort of sits, that's a index 2 normal subgroup of gamma of 2 cross gamma of 2, the thing you were expecting. So in detail, it's got an index 2 there's an index 2 subgroup of gamma of 2 with these generators, and G has that as an index 2 subgroup, and it's kind of generated by this complicated thing. And so the moduli, the conformal manifold of the aforementioned theory sits up here, and it's not a product. It's neither a product nor M05 bar. It's this thing over here. And more explicitly, it's birational to two copies of CP1. So locally, away from the exceptional divisors, I have a coordinate W on one of the CP1s and Y on the other. And there's a 2-to-1 projection to two copies of the moduli space of the four-punctured sphere, and a 4-to-1 projection to the moduli space of the five-punctured sphere. And explicitly, this is what they are. So S1 and S2, remember, were the two coordinates which told us where the two unfixed points were on the sphere. And these are squares of Y and W. And F1 and F2, I know this is a thing you can do in your head. If you plug in this expression in terms of the Y's, you get exactly the ratio of fourth powers of theta functions that I previously described. Okay, so this is the coordinatization of the actual conformal manifold for this theory, which is not quite a product theory. So that's the example to keep in mind. And the key thing, the thing that I emphasized before, but now I can make explicit, is the boundary points here. So W and Y equals 0 or infinity are points where at the boundary of M05, right? And I would have expected, oh, there should be some kind of weak coupling behavior there. Something becomes weak. But no, the gauge coupling, the two gauge couplings can be anything. They could be smack dab in the middle of the conformal manifold. So they could be at strong coupling, even though the surface has degenerated into a nodal curve. Okay, so now that was all preamble. That's introduction. Now we actually get to the talk itself about the non-abelian twists of D4. So again, I'm interested in sort of a non-trivial S3 bundle, or the isomorphism classes of non-trivial S3 bundles on this punctured curve, where I fix the bundle restricted to a little circle surrounding each puncture. S3 now acts by permutations of nilpotent orbits. Remember the things we're decorating the untwisted punctures with. And these nilpotent orbits, see, these are the very even guys, which were always exchanged by the Z2 outer automorphism, but now they come in a triple with the green guy. And to denote gamma bundles, the S3 bundles on the punctured Riemann surface, I'm going to rely on this formalism of twist lines. So the idea is, on the complement of these twist lines, you can trivialize the bundle, but when you cross a twist line, there's a transition function, some element of S3, incorporating the bundle, the restriction of the bundle to a little circle surrounding the punctures means that a twist line can end on a puncture, and the bundle restricted to that circle is the twisted sector in which that puncture lives. So let's introduce S3 twist lines. There's one for each element of the group. These three guys are order 2. These two guys are order 3. There's a fusion of twist lines, right, which just reflects the group product, right? So an order 3 guy times an order 2 guy is another order 2 guy. The product of two order 2 guys is an order 3 guy. And the product of, or the product of two order 2 guys, the square of an order 2 guy is the other order 2 guy. Right? So that's the group multiplication law. And we also have fusion of twist lines. This didn't happen in Z2, but it certainly happens in S3, where 3 twist lines can come together in a junction, and the product of the transition functions going around the junction is the identity, right? So in fact, this whole table could have been summarized by saying these are the twist lines of the twist line network. Okay. So now I want to give you some sort of a sense of why we get this interesting covering of the moduli space of punctured curves by considering the data of this bundle, this S3 bundle on it. So as I said, Dane twists will now act non-trivially on this space of pairs. And so here's a simple example, which I was, my drawing ability is rather limited, as Monica will tell you, and so this is the simplest thing I could draw. So let's take a 4-punctured sphere, let's say, right, where 2 of the guys are in this alpha-beta twisted sector, and 2 of the guys are in the alpha-beta squared twisted sector. And I draw the simplest configuration of twist lines compatible with that. Namely, I have a twist line that connects these 2 guys and a twist line that connects those 2 guys. Right? So that's a configuration of a 4-punctured sphere with punctures in these particular twisted sectors, and S3 bundle on it compatible with that. And now, the first thing I'm going to do, just for ease of drawing, is fuse these 2 lines together in the middle, okay, using the table from the previous slide. And now what I want to do is I want to take point 1, drag it around point 3, and return it to its original position. So in terms of the moduli space of curves, I've done absolutely nothing, right? It's back where it started, okay? But let's see what happens to the bundle when I do that. So I drag it around, and it comes back to its original position, and it's kind of dragged this black line around with it, right? And so now when I use the fusion of twist lines, again from the previous slide, what I get is this configuration where red became blue and blue became green. Okay? Exercise you need colored pens, but if you have colored pens, you can do it. Okay? So you get this. And now if I do the Dane twist again, I take this blue guy, drag him around the green guy, and return him to his original position. I get this configuration of twist lines. And if I do it a third time, take this green guy, drag him around the red guy, and return him to his original position, I get back my original guy. Okay, so I have this order 3 covering associated with this one Dane twist, right? If I do the Dane twist 3 times, I get back the original bundle. But if I do it once or twice, I get some other bundle. But as I said, I cheated a little bit in drawing these pictures because I wanted to fix the bundle around each of the punctures, right? So up to isomorphism, everything I said on the previous slide is perfectly fine. But so I have this story where I like to take Riemann surfaces, chop them up into pieces, and then fit the pieces together using the plumbing construction, right? If I want to do that, I actually have to glue bundles along the circle that I do the plumbing construction. And I glue bundles, not isomorphism classes of bundles. Okay, so I really need to fix the bundle on the circle surrounding the puncture, not just its isomorphism class. So really what happens when I drag this guy around and bring him back to where he started is the color of the puncture doesn't change. So when I drew something with like a green line, which started out as having a red dot there, right? What I really get is this bundle, this configuration of twist lines, okay? So I want to preserve the color of the punctures when I do that. So I get something slightly more complicated than what I drew on the previous slide. But you have similar pictures for all of the Dane twists that you can do. And because the superconformal index is constant on the conformal manifold, this kind of story yields all sorts of interesting identities between the superconformal indices in different twisted sectors that are explained in excruciating detail in our papers. Okay, so let me warm up with the once punctured torus. And we'll take the once punctured torus with an untwisted puncture, okay? Just something from the good old untwisted sector. And I claim there are 5 orbits of this in this moduli space of pairs. One of them is the untwisted thing, where the conformal manifold is just the moduli space of the once punctured torus. The other one is where I have a twist. A representative is where I have a twist in the alpha sector around, say, the A cycle, okay, and all of the modular transforms of that. That gives me a copy of the upper half plane modulo gamma 0 of 2, or its compactification. And there are 3 such orbits because there are 3 conjugacy classes here which don't get mixed. And there are 2 distinct weak coupling limits associated to each of those. Or I could have a beta twist around, say, the A cycle, in which case I have the upper half plane modulo gamma 1 of 3. And again, there are 2 distinct weak coupling limits. So, okay, that sounds very abstract. Let's take the simplest possible thing. So we'll take the simple puncture in the untwisted D4 theory, right? So that's the subregular orbit of D4, which is the partition 5, 3. If you spend any time in the subject, you know that's some kind of spinate gauging of the E8 rank 1 Minahan-Nemeshansky theory. Oh, Lord, I've got to move fast, huh? But in fact, there are 5 distinct index 2 spinate subgroups of E8, and I've listed the decomposition of the adjoint here. And so the untwisted case, the first one here, the flavor symmetry group is the unbroken group has a U1 cubed flavor symmetry. In this sector, we get a U1 flavor symmetry, but there are 3 different such theories and 2 distinct weak degenerations of the torus, which give 2 distinct weak coupling presentations. And in the beta-twisted sector, the flavor symmetry, there's no continuous flavor symmetry. And again, there are two distinct limits. M04 bar, there's 4 orbits, 3 copies of the trivial thing, and one 24-fold cover of M04 bar. And I will now give you a very curious example of that. Here's for any value of n, v, n, s, and nc that add up to 6, we get a conformal, a Lagrangian n equals 2 superconformal theory with a spinate gauge group, all of which have class S realizations of one sort or another. But let's focus on the case where 2 of these guys are 3 and the other one is 0. Here's a realization in the untwisted sector. And at the 3 special points at the boundary of the moduli space, I get 3 distinct weak coupling descriptions listed here with gauge group spinate, G2, or SP2. And I'll note that the spinate appears just once with 8s and 8c. I don't see 8v and 8s or anything like that. Those are disconnected copies of the moduli space because, as I said on the previous slide, there are 3 distinct orbits. And this is one of them. But there's also a non-abelian twisted realization written here, where S is, again, the cross ratio. And the conformal manifold is some rather complicated cover that I don't want to describe, but which factors through the upper half plane modulo gamma of 4 and projects either to the space of gauge couplings described on the previous slide or to the cross ratio, space of cross ratios over here via these 2 distinct maps. And you can see at the 6 cusp points of upper half plane modulo gamma of 4, I get different behaviors. And I want to emphasize that at this cusp point, I get some strongly coupled theory in the middle of the space of gauge couplings. And the actual thing is some slightly more complicated, well, sorry, that was not one of it, a covering of this space that I'm not going to try to explain at the moment. More generally, if I take 4 punctures in the alpha twisted sector, I will find at least 6 distinct weak coupling descriptions in this one-dimensional conformal manifold, which is rather exotic. So here's some randomly chosen example. Here's again the cross ratio. For the boundary points are when the cross ratio is 0, 1, or infinity, but there are 6 different cusp points in upper half plane modulo gamma of 4, and those give you 6 different realizations as a weakly coupled gauge theory with some exotic matter. I know of no examples where you get a Lagrangian field, purely Lagrangian field theory out of this. They always involve some isolated SCFT. But again, the different gauge groups all the way along. And I guess this is probably, I was told that I'm done, yeah. The D4 theory is, as I've emphasized, the unique case where the outer automorphism group is non-abelian. Technically, that makes the business of chopping the surface up into pieces and gluing them together by the plumbing construction rather more complicated. But it's a finite problem which has been solved, so that's not really an issue. But putting the pieces together results in much more intricate physics and much more intricate conformal manifolds than we've seen previously. And so that's where I'd like to end.